Hi all, today we are going to discuss about Maxwell-Wiens bridge, or it is also called as Maxwell's inductance capacitance bridge. So this bridge is used for measurement of self-inductance of medium Q coils. That means Q means the quality factor, the coils which are having medium quality factor, that means the quality factor lying between 1 to 10 by comparing with a standard variable capacitor. So in the last class we have seen the Maxwell's bridge. In the case of Maxwell's bridge, the unknown inductance is measured in terms of known value of inductance, but the problem there is two inductance are there, so automatically the flux that is produced by one inductor can link with the second inductor or may create the mutual inductance, and that creates the problem in the measurement. So in order to avoid that problem, here we are going for the capacitor, because the advantage of capacitor is the capacitor will be of very compact size and the capacitor does not radiate any type of the flux outside this capacitor. So because of that reason, the shielding of the capacitor also will be easy, and the second one, even the size of the capacitor is smaller when compared to that of variable inductor. So because of these advantages, so this method is used in practice instead of the method that is discussed in the last class. So let us take for example, here the L1 is the value of the unknown value of inductance and R1 is the effective value of the resistance of this inductor L1, and let us assume this R2 and R3 are the standard non-inductive resistors. Generally they are taken as the constant values out of the values 10, 100, 1000 or 10,000, which are also called as a decade resistor. In terms of 10 will be there. So because of that, the calculation will be easy. So the reason for this I am going to explain after the derivation. So after that, this R4, because here R4 is a variable resistor and C4 will be variable capacitor. So let us try to derive this case, which is the case that is shown in every textbook. So after that we will show the practically how the circuit will be there, and we will solve some numerical that came in previous IAS exam, so that this concept will be completely clear to you. So let us proceed further. We know under balanced conditions, because obviously the current passing through this detector ID will be equal to 0. So ID will be equal to 0. So this indicates the value of potential difference between these 2 points. That means if you are representing this by A, B, C and D, so potential difference between B and D will be equal to 0. Only in that case the detector current will be equal to 0. So what is the meaning that potential of B is equal to potential of D? So we can tell that the potential of AB is equal to potential of AD, and the potential between B and C is equal to potential between D and C. Or otherwise we can tell that the potential value, potential difference E1 will be equal to E2, and similarly E3 will be equal to E4. So in that case no current will pass through the detector. No current will pass through the detector. So that means I can represent this as E1 will be equal to E2. Or what is E1? E1 is nothing but I1 multiplied by Z1, and E2 will be I2 multiplied by Z2. Agree with me? So this will be I1 multiplied by Z1, I can write as R1 plus J omega L1. This will be equal to I2 multiplied by, what is Z2? It is having pure resistance. So that's why it is I2 multiplied by R2. So let us take it as equation number 1. So similarly, I can tell that the value of E3 will be equal to E4. So when E3 is equal to E4, that means that this implies that I3 Z3 will be equal to I4 Z4. So from this I can tell that I3 is nothing but, because here itself we will write it. So since the value of I3 will be equal to I1 under balanced condition, and the value of I4 will be equal to I2. So that's why this I can write as I3 is nothing but equal to I1 multiplied by Z3. Z3 is equal to R3. This will be equal to I4 multiplied by Z4. So I4 is nothing but equal to I2, and this will be multiplied by Z4. So let us try to calculate the value of Z4. So in order to calculate the Z, this is nothing but the parallel combination. So parallel combination, we know that 1 by Z4 will be equal to, because it is a combination of 1 by this one plus 1 by this one impedances. So this will be 1 by R4 plus this will be J omega C4. Because C4, because the reactance or impedance of this capacitor will be equal to 1 by J omega C4. So 1 by impedance, that will become equal to J omega C4. Or from this I can write my value of Z4. So Z4 will be equal to R4 divided by 1 plus j omega C4 into R4. How this came? So take the common, this will become equal to denominator become R4. So this will be multiplied with R4 here, that is 1 by Z4. So from this, Z4 will be equal to this one. So this I am taking as equation number 2. So that I am substituting here. So this will become I2 multiplied by R4 divided by 1 plus j omega C4 into R4. So let us take it as equation number 3. Let us take it as equation number 3. So let us try to draw the phasor diagram. So then we will proceed further for the remaining things. So for drawing the phasor diagram, so again I have to take some current as a reference. So let us take the current I1 as my reference. So I am drawing the waveform. So I am taking, let us assume the current I1 I have taken as reference. So automatically the voltage drop due to the resistance R1 will be in phase with this current, because you can see here I1 multiplied by R1 plus j times of I1 multiplied by omega L1. So this will be, I am writing here, this will be I1 multiplied by R1. So for this we have to add j times of, so for this I have to add j omega L1 times of I1. So this entire thing is nothing but equal to I1 multiplied by Z1, or that is nothing but equal to E1. You agree with me? So we can tell that this value is nothing but equal to E1. So we know that E1 will be equal to E2. So that's why we can tell that E1 is equal to E2. What is E2? E2, it is written here, it is nothing but I2 multiplied by R2, because E2 is I2 multiplied by R2. We have derived E1, because same thing will be E2 also. So this will be equal to I2 multiplied by R2. So what is the meaning of this? The I2 is also lying in the same line, because I2 R2 will be in phase with I2. So that's why we can tell that I2 is also lying in the same line. So now this I2 I can resolve into horizontal component and I can resolve into vertical component. So this I2 I am resolving into two components. So this is the vertical component. So this vertical component is due to the capacitor. That means the current that is passing through capacitor, because you can see here the I2 is coming like this. When it passes here, it is dividing into two currents. One current is IC, another current is IR. Because we know the current that is passing through the capacitor will be this component, because I2 is sum of these two currents, IC plus IR. So which are displaced by 90 degrees. So this is IC, and sum of IC plus IR, that will be equal to I2. The reason why I am writing is this one, because the sum of IC plus IR is equal to I2. So we can write here this value of I4 is equal to I2 is equal to IC plus IR, because this is the vector sum. Okay, that is the reason I have mentioned here. So once it is clear up to now, so the IR is obtained. So once the value of the IR is obtained, so now I can calculate the value of voltage drop E4, because we can tell the value of E4 is nothing but IR multiplied by the current that is passing through this multiplied by the resistance. So we can tell this IR multiplied by R4, this is nothing but equal to E4, because we know E4 is nothing but equal to E3 also. E4 is nothing but equal to E3 also. What is E3? So E3 we have derived here. E3 is I3 multiplied by Z3, which is nothing but I1 multiplied by R3, because that also will be in phase with the current I1. You can see that is satisfying. So this I can write as I1 multiplied by R3. So we got the value of E4 or E3. We got the value of E1 or E2. Now the sum of E1 plus E1 plus E3 or E2 plus E4. So that gives my resultant value of the voltage that is applied. Agree with me? So that I am mentioning here. So let us take some color. I am taking the red color. So the sum of this E1 plus I have to add to E3. So that's why I am adding this to E3. That means for this one I have added the value of E3. So this gives my resultant value of E. E is nothing but equal to E1 plus E3, or this is nothing but E2 plus E4. Agree with me? So we got the resultant value of the voltage that is applied. I hope the phasor diagram is completely clear to you. So now I am proceeding further for the derivation for the balance equation, or how to represent the inductance in terms of the other parameters. So I am proceeding further. So under balanced condition, so we can write the product of opposite impedances will be equal to same. That means the product of Z1 multiplied by Z4. So Z1 multiplied by Z4 will be equal to, this is Z2. So Z2 multiplied by Z3. So what is Z1? Z1 is R1 plus J omega L1. This will be multiplied by Z4. So Z4 we have just derived it. What is the value of Z4? Z4 is R4 divided by 1 by J omega C4 into R4. So this will be Z2. Z2 is nothing but R2 and Z3 is nothing but equal to R3. Or from this I can further simplify it. So this I can write as R1 multiplied by R4 plus J omega L1 multiplied by R4 is equal to R2 into R3, because this denominator I am taking this side. So plus J omega C4 into R4 into R2 into R3. So here now I can compare the real and imaginary terms on both the sides. When you compare the real and imaginary terms on both the sides, I can write the value of R1 will be equal to R2 into R3 divided by R4. This way, in this form I can calculate the R1, and similarly I can calculate the value of L1 will be equal to C4 into R4 is common in both the sides, so it will cancel out. So R2 into R3, C4 into R2 into R3. So this is the balance equation we got for this. So out of this we have to take the independent terms. Which are the independent terms? So that calculation will be easy. So which are the independent terms? Independent term means any term which we are varying should appear in only one equation, so that the tuning or convergence for balance condition will be easy. So R2 and R3 is appearing in both the equations, so that should not be variable. So we can tell that this R4 and C4 are independent variables and hence used for getting balance. So they are varied to get the balance. So let us see what is the advantage of these things. The advantages of this particular bridge is inductance is measured by comparing with the capacitor, as the capacitor does not produce any external field and also compact, so it is more compact and easier to shield compared to that of inductor. And the next one, the balance equation is independent of the frequency, because you can see here in these balance equations there is no frequency term anywhere. That means it is independent of the frequency. That is the second advantage. That means it is immune to the harmonics. It is not going to affect by any noise or any disturbance that is introduced. And if you are selecting the value of R2 and R3 in such a way, let us assume the product of these two terms will reach something like 10 to the power of 6, because practically we know the capacitance value generally is represented in microfarads. So microfarads means 10 to the power of minus 6 multiplied by 10 to the power of 6, because L1 is equal to C4 into R2 into R3. R2 into R3 is 10 to the power of 6 multiplied by microfarad means 10 to the power of minus 6. That means whatever is the value of C4 in microfarads, that will directly indicate the value of L1. That means we can directly measure the value of L after tuning. That means no need to make any specific calculations. If the value of R2 multiplied by R3 is taken such that that product will be equal to 10 to the power of 6. That is the advantage of this method. But there are some disadvantages also. This bridge requires variable standard capacitor. That means the capacitor should be variable capacitor, and that too it should have high accuracy. But practically if you want to get a variable capacitor with accuracy will be very costly, and even that much cost, even if you invest, there is no guarantee that we will get the proper accuracy when compared to fixed value of capacitor. For the case of fixed value of capacitor, we can get, it is assured that whatever the accuracy is mentioned, that much will be there. But variable capacitor, as the plate moves to get the variable capacitance, we cannot accurately tell that it will always maintain what value is showing there. Accuracy is very difficult task, and second one, the cost increases drastically. So that's why in practice what they will do, the value of C4 is kept constant by using a decayed capacitor. Decayed capacitor means a different capacitor will be there in that box having different values which are multiples of 10. So depending on the tuning that is required, we will select the corresponding value of C4. That means adjacent value of the C4, so that the current that is passing through the detector is less. Then C4 is not varied. Only we have selected we will select the appropriate value of the capacitor to get the proper balance. So after that only what we will do, only the value of R4 and R2 or R3, any one of them are varied to get the balance. So to understand this, we can go here, L1 is equal to R2 into R3 into C4. I told you C4 is maintained constant. So what should be varied to get the value of L? Further tuning, either we have to vary R2 or R3. So get the proper tuning for the value of L1. So that's why either R2 or R3 will be varied. Similarly, for calculating R1, R1 is equal to R2 into R3 divided by R4. So here by varying R4, we can get the proper tuning. But here the problem is, whenever you are doing the tuning, that means when you vary the value of R2, this equation is also affected and this equation also affected. So that's why the convergence will be very slow for getting the final output, so or final balance. But this convergence will be fast if your value of the quality factor of your coil is lying between 1 to 10. If it is lying less than that or greater than that, in that case the balancing will be difficult. The reason I am going to explain. So we know the quality factor of the coil will be equal to omega L1 divided by R1. We have seen what is the quality factor of the coil in basic electrical engineering playlist. You can please check there if you have doubt. So omega L1 by R1 will be equal to, you can represent even in terms of capacitance, this will be omega C4 into R4, because in that capacitor circuit C4 is connected in parallel to R4. So that's why the quality factor of that particular set will be equal to omega C4 into R4. So now let us see what are the limitations, why it is only limited between 1 to 10, what will happen if it is beyond 10 or less than 1. So for measurement of high Q coils, so high Q coils means the Q value greater than 10, this requires a large value of R4. You can see the Q is equal to more. When Q is more, you can see Q is equal to omega C4 into R4. R4 is adjusted for balance. When Q is equal to more, the automatically R4 required will be very high. And you know that the R4 is a variable resistor. So the amount of the variable resistor should be in the range of 10 to the power of 5 to 10 to the power of 6. So in this much high value, fine tuning of the resistance value or getting a variable resistor of this much high rating is very costly and very difficult. And we cannot assure the accuracy of the instrument. So that's why we cannot use it for measuring high Q values. I think high Q values is clear to you. So now let us go to measuring the low Q value. That means if the Q value is less than 1, so this Q value means Q is nothing but omega L divided by R. Q is less when L is less compared to the resistance. Q will be less when L is less compared to the resistance. So where this case will become? So this case will come for the case of inductive resistors or radio frequency coil. That means this coil will operate at radio frequency. That means very high frequency. At extreme high frequency, omega will be high. So automatically inductive reactance will be very high. But during measurement, if you are testing with low frequency signal, that means your source is of a low frequency signal, but actually that coil actually operates at the high frequency. That means when you decrease the frequency, what will happen to omega L? Omega L will decrease, but resistance is independent of frequency nearly. So that's why resistance remains same, but reactance decreases. So because of that, what happens? This Q is equal to omega L by R. Here R is dominating when compared to omega L, because you are operating that coil for a low frequency. So omega L will be less. So in that case, getting the balance by varying the value of R2 and R4 alternately will be very difficult as to get the convergence, because even if you vary by a small limit to small value, still the entire thing will disturb, and getting the balance takes so much time. That means it is so much cumbersome process, and there is no guarantee you will get the convergence within less time. So that's why generally for low value of the Q coils as well as the Q coils greater than 10, we don't go for this method. We go for the other methods which we are going to discuss in the coming lectures. So let me again explain why the Q value greater than 10 is not measurable. When the Q value is more, automatically the value of R that is required will be more, because as per this Q factor formula, you can see omega C4 into R4. So R required will be very high, and that too we want a variable resistor because we do the tuning of R4. So getting that variable resistor for this much high rating will be very costly. And second one, there may be, it may not be properly accurate also. So that is the major disadvantage of this. That's why for Q values greater than 10, it is not proper, and for Q values less than 1, getting the balance is difficult. Because of these two reasons, always this method is used for Q coils from 1 to 10 rating. So let us take one example that is given in the IES exam, so which deals with varying some other parameters instead of capacitor. So it came in IES 2001 in electronics paper. So in a Maxwell's bridge shown in the figure, the fixed value bridge components have the following values. So they have mentioned the value of R3 is equal to 5 ohms. The value of R3, that means this R3 they have fixed as 5 ohms, and C they have fixed as 1 millifarad. Calculate the value of LU and RU. These are the unknown value of reactor and its resistance. And they have varied the value of R1 and R2, because practically if you are varying R1 and R2 both the values, it is very difficult to get convergence. But in this case, due to some reason, they have varied R1 and R2 only, and it is mentioned that when the R1 is equal to 159 ohms and R2 is equal to 10 ohms, they obtain the balance condition. So it is asked to calculate what is the value of LU and RU, and also calculate the Q factor of the unknown impedance at supply frequency of 50 Hz. This is what is asked. So let us try to calculate these things. So I am directly using the formula, because instead of deriving everything again, we know the balance equation R will be equal to R1 R2 divided by R3. So R1 into R2 divided by R3, because product of these two divided by this one. So I am directly substituting. So this will be 159 multiplied by 10 divided by 5. So if you calculate this, you will get it as 318 ohms. So we get the value of RU. So similarly, we can get the value of LU will be equal to C multiplied by these two resistors we have to multiply. So this is R1 multiplied by R2. And one thing I want to tell you, no need to mug up any formula. Even you can derive these things easily in the exam. Only one thing is you should know how the different components are connected. Once you remember that, derivation you can do even in the exam. It will take only 2-3 minutes. So C into R1 multiplied by R2. So the value of C is mentioned there as 1 millifarad. So 1 into 10 to the power of minus 3 multiplied by R1 multiplied by R2. So what is the value of R1? This is 159 multiplied by R2 is 10. So this you will get as 1.59 Henry. So 1.59 Henry came. So now let us calculate the Q factor. So for calculating the Q factor, either we can calculate by omega L divided by R of the respective coil, or second option is there, we can calculate from here also. This I can calculate as omega C multiplied by R3. So you can calculate using any one of these two, you will get the same answer. So we know omega is equal to 2 pi f. This will be equal to 2 pi multiplied by 50. This will be multiplied by 1.59, because LU is 1.59 divided by RU. RU is 318. So this will be equal to 1.5708. So in this way you have to calculate. I hope this Maxwell's inductance capacitance bridge or Maxwell's Wien bridge is completely clear to you. If you still have any queries, you can leave your comments in the comment section below. I will answer to your queries from there. Thank you very much.